All right, let's dig into this. If you're working in AI research, you know the feeling. It's just moving incredibly fast.
Oh, absolutely. Keeping up with all the new papers is, it's a real challenge, just a flood of information.
Yeah, trying to find the time, let alone figure out which ones have those key breakthroughs.
Exactly. So for those of you trying to stay on the cutting edge, we're doing a deep dive today into a really interesting preprint.
Okay, what do we got?
It's called OTC, Optimal Tool Calls via Reinforcement Learning. It's by Wang and colleagues from several top institutions, still under review, so it's hot off the press.
OTC, optimal tool calls. Okay, so give us a quick version first, the 1-minute summary for folks short on time.
Sure. So the main issue is that LLMs using external tools like search or code execution often aren't very efficient. They make too many calls, sometimes not enough.
Right, cost time and money.
Exactly. So this paper introduces something called OTCPO, Optimal Tool Call Controlled Policy Optimization. It's a new RL framework. And the key thing is a new reward system. It pushes the model to get the right answer, but using the fewest tool calls possible. They call this boosting tool productivity.
Tool productivity, got it.
And their experiments using Quen models show they can significantly cut down tool calls, boost that productivity measure, all while, crucially, keeping the accuracy pretty much the same on QA tasks.
Okay, interesting. Big efficiency gains without sacrificing the quality.
That's the core pitch.
So our mission for this deep dive is to really unpack this OTCPO. How does it actually work? Why is optimizing tool use so important for AI systems moving forward?
And what do these results really mean if you're, say, an ML engineer thinking about practical applications?
Exactly. Let's get into it.
Okay, so let's set the scene first. The concept is tool integrated reasoning, or TIR.
Right, giving LLMs tools like search engines, calculators, code interpreters, things like that.
Precisely. It lets them do stuff beyond just manipulating language, accessing real-time info, doing calculations,
Stuff they can't just know internally. But you mentioned earlier, current RL methods for this have limitations.
Yeah, I mean, they've definitely made progress in teaching LLMs to use tools better, but the main reward signal has often just been, did you get the final answer right, yes or no?
So not much focus on how it got the answer.
Not enough, yes. Yeah. Especially not on the number of times it called a tool. And this sort of indiscriminate tool use can cause problems.
Okay, like what are the downsides if the model is just calling tools left and right?
Well, first off, there's the obvious computational and time overhead. Every tool call takes resources, takes time.
Which adds up fast if you're running this at scale, thinking about deployment costs.
Definitely. Big cost implications. And second, the paper brings up this idea of cognitive offloading.
Cognitive offloading.
Yeah, like if the model always reaches for a tool, even when it might be able to figure something out internally, it might not develop its own reasoning abilities as strongly.
Like using a calculator for simple addition all the time. You kind of forget how to do it in your head.
That's a good analogy. And this might be especially true for bigger models that should, in theory, have more internal reasoning power.
Right. So it's inefficient now and potentially hinders the model's own capabilities long term.
And it leads to these inefficient reasoning behaviors, either using tools way too much, even when not needed, or sometimes not using them enough when they're actually crucial.
Okay.
Now, a key idea in this paper, a sort of foundational assumption, is that for any given question and a specific model, there's probably an optimal number of tool calls needed for a correct answer.
Optimal meaning minimal, the fewest possible.
Exactly. The fewest calls to get it right. And critically, this number isn't fixed. It depends on the model itself.
Like a smaller model might need more searches than a huge one.
Right. And it depends on the question's difficulty, too.
Okay, that makes sense. So it's variable.
It is. And this is where traditional supervised fine-tuning, SFT, often struggles. SFT tends to push for a more uniform way of using tools.
Like a one-size-fits-all policy.
Yeah, which doesn't really capture this variability. Reinforcement learning, though, is more flexible. You can design rewards to encourage not just correctness, but also efficiency getting there with fewer tool interactions.
Which brings us back to OTCPO. How does it actually achieve this? What's the core mechanism?
Right, so OTCPO uses RL to train the models to be much more precise and adaptive in how they use tools. The real innovation is this new reward system.
The tool integrated reward you mentioned.
Exactly. It modifies the usual rewards like correctness by multiplying it with a factor that reflects how efficiently the tools were used.
So, like, you get points for being right, but more points if you were right and efficient.
Kind of, yeah. It encourages getting the right answer with the minimum tool calls. They frame this around tool productivity.
Cool productivity again, so that's the ratio.
Benefit accuracy divided by cost number of tool calls. OTCPO tries to maximize that ratio.
So, getting it right efficiently, like finding the quickest route on a map, not just any route.
That's a great way to put it. And importantly, they mention it's designed to be lightweight. You can plug it into existing RL pipelines.
Like PPO and GRPO, they mentioned those.
Exactly. Proximal policy optimization and generative reward policy optimization. It integrates with those.
Okay, so you have OTCPO and OTCGRPO. How are they different in how they implement this?
Good question. Let's start with OTCPPO. PPO works by looking at individual trajectories, single attempts to solve the problem.
Right.
So they designed a tool reward function based on just the calls within that one try. It's a cosine function. Our tool, it goes m pi 2 meters plus c.
Whoa, okay, math. Break that down. M is
the number of tool calls in that trajectory. C is just a small constant to keep things smooth.
So as M, the number of calls goes up.
The value inside the cosine increases, and the cosine value itself goes down. So more calls means a lower R tool reward.
Penalizing more tool use within that single attempt.
Precisely. But because PPO only sees one path at a time, figuring out the true minimum needed might take a while. It's sort of an approximation based on individual runs.
Okay. So how does OTCGRPO improve on that?
GRPO looks at a group or batch of responses generated for the same prompt.
Ah, okay. Multiple attempts at once.
Yes. And within that batch, it first identifies which attempts actually got the right answer.
Filters for the successful ones.
Right. Then, among those successful ones, it finds the attempt that used the fewest tool calls. Let's call that minimum number K.
So K is like the best observed minimum for that batch.
Exactly. It serves as a local estimate for the optimal number of calls, which they call N. And they mention you could even update this K across batches to get a better global estimate of N over time.
Okay, so it's using the batch to get a better sense of what the true minimum N might be.
That's the idea. And based on this estimated N and the actual calls M in a specific trajectory, OTCGRPO uses a more sophisticated piecewise reward function.
It's piecewise, meaning it behaves differently in different situations.
Correct. So if the estimated optimal N is 0, meaning the model should be able to answer internally,
then making 0 calls, N gets the highest reward.
Yes. And if N is 0, but the model did use tools, M0, it uses that same cosine function from OTCPPO to discourage it.
Okay. But what if the optimal N is greater than 0, if tools are needed?
Then it uses a different function based on sign, sin fmm pi 2n. Here, fmn is just a way to adjust m. The really key part is that this function is designed so the reward peaks when m, the actual calls, is equal to n, the estimated optimal number.
Oh, so it's not just fewer calls is better, it's hitting the right number of calls is best.
Exactly. It's rewarding precision, not too few, not too many, just right.
The Goldilocks number of tool calls?
You could say that. And finally, both methods combine the SAR tool with the standard reward, R phi, like correctness, using multiplication. R tool phi, alpha, R tool, R phi.
Alpha is just a weighting factor.
Yeah, a hyperparameter to tune. But the multiplication is important.
Why is that?
Because if the answer is wrong, R phi is 0, right?
Right.
So the whole final reward becomes 0, no matter how efficient the tool use was. It prevents the model from just learning to use 0 tools and always being wrong, but still getting a high tool score.
Ah, clever. It ensures accuracy is still the main gatekeeper. You only get the efficiency bonus if you're actually correct.
Precisely. Avoids that kind of reward hacking.
Okay, the mechanisms make sense now. OTCPPO penalizes more calls, OTCGRPO tries to hit the optimal number based on batch performance, and the final reward ensures accuracy isn't sacrificed. So how did it perform in practice? They tested it with search as the tool first?
They did. They used standard data sets like NQ, natural questions, and Hotpot QA, and they compared against several baselines, SFT, RAG, ERRkey, and importantly, search R1 PPO, which is a strong RL baseline for this kind of task.
And the results. Table 1 had the main findings for the Quinn models, right?
Yes, for the 3 billion and 7 billion parameter crew models, and the results were pretty striking.
Lay them on us.
Okay, so compared to that search R1 PPO baseline, both OTCPPO and OTCGRPO significantly reduced the number of tool calls.
How significant?
Reductions up to 73.1% in some cases. Huge drop.
Wow.
And at the same time, that tool productivity metric we talked about, it shot up. Increases of up to nearly 230%.
Whoa. So way fewer calls, much higher productivity. What about accuracy? The exact match scores.
That's the interesting part. They were mostly comparable. The smaller 3B model saw maybe a slight dip in EM with OTC,
Yep.
but the larger 7B model basically maintained its accuracy level compared to the baseline.
So especially for the bigger model, massive efficiency gains with almost no accuracy loss. That's impressive.
It really is. You can see it visualized nicely in Figure 1 as well. OTCPO matching the final performance of Search R1 on the 7B model, but clearly using tools much more efficiently along the way.
Gotcha. And they noticed something about model size in the baseline, too.
Yeah, an interesting side note, in the Search R1 baseline, the smaller 3B model actually used fewer tools than the larger 7B one.
Huh. You might expect the bigger model to need fewer tools because it knows more.
You might, but this suggests that without a specific penalty, larger models might just default to relying more heavily on external tools, maybe just in case.
Cognitive offloading again.
Could be. But the good news is, when they applied OTCPO, the reduction in tool calls and the boost in productivity were even larger for the 7B model compared to the 3B.
Suggesting the method scales well. It's maybe even more beneficial for bigger models that tend to overuse tools.
That seems to be the implication, yeah. Good scalability.
Okay, that's search. Did they look at other tools? You mentioned code earlier?
They did, briefly. Table 2 shows some preliminary results using code execution as the tool on the A benchmark datasets.
Similar story.
Pretty much.
Mm-hmm.
Even without heavy tuning for that specific task, they saw similar trends, fewer tool calls, better productivity compared to the TARL baseline they used there.
Okay, so the core idea seems transferable, at least preliminarily.
It hints that way, yes.
So, beyond the numbers, how did this actually change how the models behaved? Did they analyze the process?
They did. Figure 3 looks at the training process itself. It shows the OTC methods getting to similar performance levels.
But with fewer tool calls, you said.
Fewer calls and also generating shorter responses overall. And interestingly, Figure 3B suggests it might even speed up the training optimization itself in terms of actual runtime.
Faster training and more efficient inference. That's a double win.
Definitely appealing from a practical standpoint. Then they looked at inference behavior more closely in Table 3, categorizing the outcomes.
Okay, what categories?
Category A was cases where OTC got the same correct answer as the baseline, but used fewer tool calls.
That was common.
Happened around 80% of the time, they said.
Wow, okay. So mostly just being more efficient.
Then there was Category C, which is maybe even more interesting. These were cases where the baseline failed to get the right answer, but OTC did get it right, and did so using fewer tools than the baseline attempted.
So not just more efficient, but sometimes actually better at solving the problem too.
In some instances, yes. It suggests the more targeted tool use might lead to better outcomes sometimes.
What about Category B?
That was where OTC used more tools but got the same correct answer. They noted this happen, but less frequently than the other categories.
Suggesting it's not perfect, but the overall trend is towards better efficiency.
Exactly. A better balance. The takeaway is that OTC isn't just making things cheaper. It seems to be encouraging smarter, more effective tool use overall.
Smarter, not just fewer. Okay. And did this improve deficiency and behavior generalized? Did they test it on data sets it wasn't specifically trained on?
Yes, that's crucial for seeing if it learned a general strategy. Figures 4 and Table 4 show results on out-of-domain QA datasets like Trivia QA, Pop QA, 2Wiki, Music, Bamboogle. A good mix.
And how did OTC fare there?
Generally very well. Across the different models and benchmarks, the OTCPO methods usually achieve the highest tool productivity scores.
Better generalization and efficiency.
Yes, and often OTCGRPO edged out OTCPPO in terms of productivity on these new data sets.
Suggesting that batch-based estimation of N might be more robust.
Potentially, yeah. And another interesting point, for the 7B model, OTCPPO sometimes even beat the Search R1 baseline on accuracy, exact match on these new data sets.
While still using fewer tools.
While still using significantly fewer tools. So it hints at better generalization and accuracy as well, not just efficiency.
That's really promising. It's learning a more fundamental skill.
It seems that way, and the case studies they included really drive the point home.
Right, figures 5, 7, and 8. What do they show?
So Figure 5 is a great example. The baseline Search R1 makes like multiple search calls that seem a bit redundant.
Okay.
OTCPPO gets the same answer but with just one more focused search call.
More efficient.
And then OTCGRPO, in this case, actually figures out the answer using its own internal knowledge. No tool calls needed at all.
Wow. So it really shows that spectrum, from redundant calls to efficient calls to no calls if possible.
Exactly. It highlights how OTC encourages leveraging internal reasoning when possible. Then Figure 7 shows another case where OTCGRPO answers correctly using internal knowledge.
While the baseline wastes time with unnecessary searches.
Precisely. And Figure 8 shows a slightly different scenario where both get it right, but Search R1 makes several, maybe less effective calls, while OTC-GRPO makes just one call, but it seems more targeted and effective.
So even when using tools, it's using them more intelligently.
That's the takeaway from the case studies. Minimizing unnecessary calls, maximizing internal reasoning, and making smarter calls when they are needed.
These examples make it much clearer than just the numbers.
Definitely. And one last bit of analysis looks specifically at tool overuse versus underuse using Table 5.
Okay, how'd they measure that?
They use two metrics, LT, less tools, same correct answer, and MT, more tools but getting a correct answer where the baseline failed.
LT is efficiency, MT is potentially overcoming underuse.
Kind of. Their analysis suggested that smaller LLMs, when just optimizing for correctness, might sometimes underuse tools.
Missing opportunities where a tool would help.
Yeah. While larger models, as we discussed, tend to overuse them.
Okay.
And the finding was that OTC seems to help correct both issues. It encourages the underusers to use tools when appropriate, leading to some MT cases, and discourages the overusers, leading to many LT cases.
So it pushes models towards a more balanced, more appropriate level of tool use, regardless of their initial tendency.
That appears to be the effect, leading to more balanced utilization overall.
Okay, wow. We've covered a lot: the inefficiency problem, the OTCPO solution with its PPO and GRPO variants, the tool rewards, the really strong experimental results, the behavioral analysis, generalization, case studies. Let's try and synthesize this. What are the absolute key takeaways for the AI researchers and ML engineers listening?
I think the main message is that this OTCPO framework, especially the GRPO version, looks like a really effective way to make tool-using LLMs much more efficient.
By directly optimizing the number of calls.
Right. And crucially, without really hurting accuracy, particularly on larger models. The results show big potential for reducing compute costs.
Faster inference times.
And getting models to actually use their internal smarts more effectively instead of just defaulting to a tool. These are all pretty significant practical benefits for anyone deploying or building these systems.
And it's still early days for this specific work. It's a preprint, ongoing research.
That's right. The authors mention it's ongoing, and they plan to release more details and explore extensions. So it's a promising direction with more likely to come.
Definitely something to keep an eye on. So maybe a final thought for our listeners to chew on.
Yeah.
How important do you think it will be going forward to explicitly model and reward resource efficiency? Things like tool calls, maybe compute, maybe other things as we build more and more complex AI agents for the real world.
That's a big question.
And maybe think about that balance in your own work, the trade-off between external knowledge or tools and the internal reasoning power of the models themselves. Where's the sweet spot, and how can we guide models towards it?
It feels crucial, doesn't it? As these systems get embedded everywhere, just making them work isn't enough. They need to work efficiently. This paper is a great step in thinking about how we actually optimize the process, not just the final output.
A really important shift in perspective. Well, thanks. This was a fantastic deep dive. Really fascinating to see research tackling efficiency so directly.
My pleasure. Yeah, great paper, lots to think about.
We'll definitely be watching for follow-ups from this team.